All right. Hello again. As explained in the previous video, this video is about converting from moles to mass. The previous video was about converting from moles to number of particles. Now, you'll notice that much of the text in this handout might actually look familiar, because I did take some text from Friday's handout and copied it into this handout. So basically, the first part of this handout is just a recap. And I thought it would be helpful to do a recap in the first part of this handout, just so that I could explain some of Friday's material. There was a handout attached to Friday's material that explained why the number for a mole is 6.02 times 10 to the 23. And it also explained this idea of molar mass, which we'll be making use of in this lesson. So I thought that it would be helpful for me to just spend the first part of this video reviewing what Friday's material was about, just so that you can hear me explain it. That might be a better way to learn it than just by reading handouts in Google Classroom. So yes, you'll see basically the first half of the handout roughly is a recap, and then the second half is actually about converting from moles to mass. So let's start out with our recap. Let's recap what we've learned so far about this number, 6.02 times 10 to the 23. So we learned on Friday that a mole is a counting unit. Other examples of counting units include a pair or a dozen. So if you have a pair of something, say a pair of socks, that means that you have 2 socks. If you have a dozen of something, say a dozen eggs, then you have 12 eggs. Okay, so a pair and a dozen are both examples of counting units. The mole is also a counting unit. It's just that it's a very large counting unit. In particular, the number is approximately 6.02214179 times 10 to the 23, which we often round to 6.02 times 10 to the 23. Now, as mentioned in the previous video, we have a name for this special number. It's called Avogadro's constant, and it's given this name in honor of the Italian scientist Amedeo Avogadro, which is a very Italian-sounding name. Now, 6.02 times 10 to the 23 is a very, very large number. Said out loud, it's 602 hexillion. And the reason why the number is so large is because it's used to count things like atoms and molecules. And atoms and molecules, of course, are very, very, very small. But why is this 6.02 times 10 to the 23 number used in chemistry? Well, I'll highlight the answer. This is the official answer to the question of why 6.02 times 10 to the 23 is unique. And this is a bit of a mouthful. I'll just read out loud what is highlighted here. So the number 6.02 times 10 to the 23 is unique because it is the number of particles needed in a sample for that sample to have a mass in grams that is equal to the atomic mass of the particles in atomic mass units. Now, we're going to see some examples to just make clearer exactly what that means, because I know that's a mouthful and it's kind of hard to follow exactly what that sentence is saying. Before we see some examples, though, let's just remind ourselves of how atomic mass units work. So, copper atoms have an average atomic mass of 63.546 atomic mass units. So an atomic mass unit is defined so that one atomic mass unit is approximately equal to the mass of one proton or one neutron. Okay, a proton and a neutron have approximately the same mass. They're very close to being the same. And so an atomic mass unit is approximately equal to the mass of one proton or one neutron. And so this also means that our copper atoms have an average atomic mass of 63.546 atomic mass units. This gives an indication of the number of protons and neutrons that you can find in an average copper atom. So if you add up the number of protons and neutrons for a copper atom, on average, that sum is going to be around 63.546. Okay, so 63.546 is an average. Now, the average mass of a copper atom is 63.546 atomic mass units. And here's the thing. Here's where the number 6.02 times 10 to the 23 comes in. If you had a sample of 6.02 times 10 to the 23 copper atoms, that sample would weigh 63.546 grams. So the average atomic mass for a copper atom is 63.546 atomic mass units. If you had 602 hexillion copper atoms, that number of copper atoms would weigh 63.546 grams. Now here are some other examples to just better understand how this works. A sulfur atom has an average atomic mass of 32.066 atomic mass units. I'll just mention that U is the symbol for atomic mass unit. So this is saying that a sulfur atom has an average atomic mass of 32.066 atomic mass units. So, if you had a sample of 6.02 times 10 to the 23 sulfur atoms, that sample would weigh 32.066 grams. Okay, and there is an image provided that actually shows these masses of copper and sulfur. So this beaker has 63.546 grams of copper. That is a mole of copper atoms. There are about 602 hexillion copper atoms in that beaker. This beaker has 32.066 grams of sulfur. That is a mole of sulfur. So that beaker has about 602 hexillion sulfur atoms. Okay, and you can keep going. There are other examples. A magnesium atom has an average atomic mass of 24.305 atomic mass units. And so if you had 602 hexillion magnesium atoms, that number of magnesium atoms would weigh 24.305 grams. And that's shown in this beaker. Okay, so it's important to understand that a mole of one thing has a different mass than a mole of another thing, because a mole is a counting unit. So 602 hexillion copper atoms are going to have a different mass than 602 hexillion sulfur atoms. Okay, and so this is why a mole of copper has a different mass than a mole of sulfur. And I do think that's part of what some students find a bit confusing about the mole. This idea that a mole of one thing has a different mass than a mole of another thing. But that is how the mole works. It is a counting unit. So 602 hexillion of one thing is going to have a different mass than 602 hexillion of another thing. Okay. I would ask at this point if anyone has any questions. I kind of felt like that would be a good time to ask, but this is a pre-recorded video, so I can't really do that. Okay. So that brings us then to this idea of molar mass, which I think is helpful for us to go over. So the mass of 1 mole of a substance is called the molar mass of a substance. And so in the case of copper, we've said that a mole of copper atoms weighs 63.546 grams. So the molar mass of copper then would be 63.546 grams per mole. Molar mass always has units of grams per mole. Again, it's simply the mass of 1 mole of the substance. So for copper, the molar mass would be 63.546 grams per mole. For sulfur, the molar mass would be 32.066 grams per mole. Magnesium would be 24.305 grams per mole, and so on. Now, it's very straightforward to determine the molar mass of copper or sulfur or magnesium, because all you need to do is just look at the periodic table, and the periodic table tells you the average atomic mass of copper, sulfur, magnesium, or tin atoms. Okay, so here's our periodic table, right? If I want to know what the molar mass is of copper, that's easy. I just look at the average atomic mass for a copper atom, and that gives me the molar mass. Okay, so for copper, it's 63.546 grams per mole. Sulfur, it's 32.066 grams per mole. Magnesium is 24.305 grams per mole. You know, pick your element. Aluminum, 26.982 grams per mole. That's pretty straightforward. But what if instead we wanted to calculate the molar mass of a compound? So let's say that we wanted to calculate the molar mass of water. So we wanted to figure out what the mass would be of 1 mole of water molecules. In other words, what is the mass of 6.02 times 10 to the 23 water molecules? Well, to do this, we simply need to calculate the average atomic mass of a water molecule. Okay, in the case of calculating the molar mass of copper, we just asked what the average atomic mass is for a copper atom. So if we want to calculate the molar mass of water, we just need to ask what is the average atomic mass of a water molecule. So the calculation is shown in this box, and this calculation was included in Friday's material. So calculate the molar mass of water. Well, to calculate the molar mass of water, we just need to add up the average atomic masses of the atoms that make up a water molecule. Okay, so this is saying that the molar mass of H2O is equal to 2 times the molar mass of hydrogen atoms plus 1 times the molar mass of an oxygen atom. So I'm just adding up the average atomic masses of the atoms that make up a water molecule. Okay, so what is the molar mass for hydrogen atoms? It's 1.01 grams per mole. I just rounded to 1.01. Okay, and then for oxygen atoms, it's 6.00 grams per mole. And so the answer comes out to be 18.02 grams per mole. So again, this means that if you had 602 hexillion water molecules, that number of water molecules would weigh 18.02 grams. 602 hexillion water molecules weighs 18.02 grams. So that's how molar mass works. Now, I think that it's kind of important at this point to just motivate why the mole is a useful concept. We are definitely going to be using the mole in this unit to do various calculations. Let's just look at a simple example to just get a feel for why the mole is useful in chemistry. So this is an example that we're revisiting from our lesson on Friday. So to see why the mole is useful, let's just imagine for a second that we are reacting magnesium with sulfur to create magnesium sulfide. Okay, I chose this reaction because it's very simple. It just involves one atom of magnesium reacting with one atom of sulfur to form one magnesium sulfide unit. Now, let's further suppose that we have 1 mole of magnesium. So we have 1 mole of magnesium. Now, what mass would 1 mole of magnesium have? Well, it would have a mass of 24.305 grams. Okay, and I can get this from our periodic table. Molar mass of magnesium is 24.305 grams per mole. So if I had 1 mole of magnesium, 24.305 grams of magnesium, what mass of sulfur would we need to react with the 24.305 grams of magnesium? Well, let's just remind ourselves of what a mole is. If we have a mole of magnesium atoms, that means that we have 6.02 times 10 to the 23 magnesium atoms. Now, if we have 6.02 times 10 to the 23 magnesium atoms, we would need that same number of sulfur atoms, because every magnesium atom bonds with one sulfur atom. Right? If every magnesium atom bonds with one sulfur atom, then if I have 602 hexillion magnesium atoms, I'm going to need 602 hexillion sulfur atoms. So if I started with a mole of sulfur, or of magnesium, rather, then I am going to need a mole of sulfur to react with that mole of magnesium. And so, what mass of sulfur would we need? Well, we'd need the mass of 1 mole of sulfur, which would be 32.066 grams. Okay, so 1 mole of magnesium has a mass of 24.305 grams. If I have 1 mole of magnesium, I need 1 mole of sulfur, which has a mass of 32.066 grams. So hopefully that just gives you a sense for why moles are useful. Moles basically are really large counting units that let us count the numbers of atoms or molecules in a reaction. The thing about chemistry is that chemical reactions take place at the atomic and molecular level. So in the reaction between magnesium and sulfur, the reaction involves 1 magnesium atom bonding to 1 sulfur atom. But the thing is, in the lab, we don't actually count out numbers of atoms and molecules whenever we're measuring samples of magnesium or sulfur. Instead, we just weigh samples in grams. And so when we're doing chemical calculations, it's really useful to have a counting unit that chemists can measure in the lab. And so the mole is such a unit. when I have a sample of 24.305 grams of magnesium, you know how many atoms of magnesium are in that amount. There are 602 hexillion atoms. And so those 602 hexillion magnesium atoms will react with 602 hexillion sulfur atoms, which we can know immediately have a mass of 32.066 grams. Okay, now if you didn't quite follow all of that, it's kind of complicated. We are going to return to these sorts of calculations later in the unit. This was actually a very simple example of a stoichiometry calculation, and there's an entire part of this unit about stoichiometry, and we're going to do some more complicated examples. So we're definitely going to return to stoichiometry later. But I just like to include this explanation to just show students why the mole is useful. Okay, I know this video is kind of long, but it's long because we had to review some of Friday's material. We're now in a position to actually get into today's stuff, which is on converting from moles to mass. Now, I anticipated it would take me a while to just review Friday's stuff. So, this material on converting from moles to mass is not very long. There's a couple of examples, and then you'll have an opportunity to try some examples yourself. All right. So yes, in our previous lesson, we looked at examples where we were converting from moles to number of particles. So now we're going to learn how to convert from moles to mass. And to do this, we need to make use of this molar mass idea. Okay, so we calculated earlier that a mole of water weighs 18.02 grams. So if you had 602 hexillion water molecules, you would have 18.02 grams of water molecules. Now, if you instead had 2 moles of water molecules, how much would the 2 moles weigh? Well, that's easy. If 1 mole weighs 18.02 grams, to find the mass of 2 moles, I just need to multiply it by 2. So we take our 2 moles, multiply it by the mass of 1 mole, which is 18.02 grams per mole. And the answer comes out to be 36.04 grams. Now, similar to what we had seen in our previous lesson, we actually just did a calculation with moles. And this calculation is going to help us arrive at the relationship that we'll be making use of in this lesson. So as we saw before, the number of moles is denoted by a lowercase n. So we have a lowercase n symbolizing the number of moles. Molar mass is denoted by a capital M. And so in this example, the molar mass is 18.02 grams per mole. So that's our capital M. And then the mass of the sample is denoted by a lowercase m. So in this example, the mass of our sample was 36.04 grams, so that would be our lowercase m. So it's important to understand that when we're doing these calculations, a capital M is very different from a lowercase m. So the capital M is molar mass. It has units of grams per mole. But the lowercase m is just the mass of the sample, so it has units of grams. Okay, so whenever we performed our calculation, we multiplied the number of moles by the molar mass to get the mass. So like we saw before, we can equivalently write this relationship in terms of the number of moles. If we just solve for the number of moles, we get N equals lowercase m over capital M. That's the relationship that we're going to put to use in this handout. And let's look at how these examples work. In our first example, it asks what amount in moles is 15.3 grams of sulfur dioxide. To solve this, we're going to use the relationship that we just saw. The relationship being that the number of moles equals the mass over the molar mass. Now you'll notice here that I put an SO2 subscript. So this is simply to show that the number of moles of sulfur dioxide equals the mass of sulfur dioxide over the molar mass of sulfur dioxide. There will be problems that we'll solve where we'll be dealing with different substances. In this problem, we're just dealing with sulfur dioxide, but in other problems, it will definitely be useful to have subscripts to just keep track of what number of moles we're talking about here, whether it's the number of moles of sulfur dioxide or some other substance. So yes, this is our relationship. The number of moles of sulfur dioxide equals the mass of sulfur dioxide over the molar mass of sulfur dioxide. This problem is asking for the number of moles of sulfur dioxide. Right, so it's asking what amount in moles is 15.3 grams of sulfur dioxide. So we're looking for this variable, the number of moles. That number of moles is equal to the mass over the molar mass. Now we know the mass, that is given. We know that the mass is 15.3 grams. To solve this problem then, we need to determine what the molar mass of sulfur dioxide is. So once we know that molar mass, we're in a position to calculate what the number of moles is. We've seen before how this works. We calculated the molar mass of water earlier. So we're going to apply the same approach to calculate the molar mass of sulfur dioxide. The molar mass of sulfur dioxide would be equal to the molar mass of sulfur atoms plus 2 times the molar mass of oxygen atoms. And then the molar mass comes out to be 64.07 grams per mole. Now with that molar mass, we're in a position to solve for the number of moles of sulfur dioxide. So here we're taking the mass of sulfur dioxide and dividing by the molar mass. The mass is 15.3 grams. We divide by the molar mass, 64.07 grams per mole. And the answer comes out to be 0.239 moles. That is the number of moles in 15.3 grams of sulfur dioxide. Again, I would ask at this point if there are any questions, but it's a pre-recorded video, so hopefully that made some sense. If there are any questions, of course, just feel free to reach out. Now, the second example is a little different. We're still making use of the same relationship that we saw. It's just that we're solving for the mass instead of the number of moles. So the example says, a chemist performs a reaction that produces 0.258 moles of silver chloride precipitate. What mass of precipitate is produced? So as before, we're going to write our relationship. We know that the number of moles of silver chloride equals the mass of silver chloride over the molar mass. But again, in this example, we're not actually solving for the number of moles. We're solving for the mass. In the first line, I'm multiplying both sides of the equation by the molar mass. That gets the mass of silver chloride on its own. And so that gives us that the mass equals the number of moles times the molar mass. So I'm just solving for the mass in these lines. Just isolating the mass, getting it on its own. Now, the mass is equal to the number of moles times the molar mass. We know that the number of moles is 0.258. That is given in the problem. And so we need to determine the molar mass of silver chloride to solve the problem. If we know the molar mass of silver chloride, then we multiply it by the number of moles to get the mass. So that's what I'm doing here. I'm calculating the molar mass of silver chloride. It comes out to be 143.32 grams per mole. With that, we can then solve for the mass. So here I'm taking the number of moles and multiplying it by the molar mass to give a mass of 37 grams. So 0.258 moles of silver chloride weighs 37 grams. That's what we calculated. Okay, as I said before, feel free to reach out if you have any questions about this. It is not ideal for us to be covering this material about moles asynchronously, but hopefully that made some sense. There is an opportunity for you to try some examples on your own. There are 6 examples that all involve either converting from the number of moles to mass or vice versa. So the questions are given along with the answers, like in our previous handout on converting from moles to number of particles. Okay, so that's it for today's material. Again, feel free to reach out with any questions, but yes, the next task for you to do is to just work through these examples, and that's it for today.